Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. In this video, I will explain about chapter 13. But the first, I want to introduce myself. My name is Putra Hutabarat with study ID number 23055311075. I am from Mechanical Engineering study program from Engineering of Fakultas Udayana University. This is main referency Metallurgy for the Non-Metallurgist second edition. Okay, next chapter 13. Non-ferrous metal, a variety of feasibilities compared with their steel counterparts. Non-ferrous metals and alloys are notable in their number and in the diversity of their properties. Many non-ferrous elements do double duty as important alloying agents for both steels and non-ferrous metals. For example, virtual all steels contain small amounts of manganese, which is used mainly to control and in some cases counteract the undesirable effects of sulfur and to aid in achieving hardenability requirements. The latter approach was chosen in this chapter, where several non-ferrous metals are grouped into the following key alloy categories, like metals: aluminium, beryllium, magnesium, and titanium. Corrosion resistant alloys, that is copper, nickel, titanium, aluminium. Super alloys, that is nickel, cobalt, iron, nickel. Refractory metals: molybdenum, neodymium, rhenium, thallium, and tungsten. Low melting point metals: bismuth, indium, lead, tin, zinc. Reactive metals: hafnium, titanium, and zirconium. Precious metals like gold, silver, platinum, palladium, iridium, rhodium, ruthenium, and osmium. Rare earth metals: semi-metals, also known as metalloids. Next, 13.1 Light metal. High strength, lightweight alloys are of great importance in engineering application for use in land, sea, air, and space transportation. 1 kilogram or 2.2 lb of metal saved in the design and construction of such a system can result in important weight saving in power plants, transmission system, and in total fuel requirements. There is a strong demand for high strength, lightweight metals and alloys. This is the table 13.1. The metal commonly classed as light metals are those whose density is less than the density of steel, or 7.8 gram per centimeter cc, or 0.28 lb per in 3.3, and whose properties meet the requirements for specialist engineering applications. The density and elastic models of 4 important metals in this group are listed in table 13.1. Next, magnesium, or Mg, has long been recognized as the lightest structural metal. Structural applications include industrial materials handling, commercial and aerospace equipment. In industrial machinery, such as textile and printing machines, magnesium alloys are used for parts that operate at high speeds and thus must be lightweight to minimize inertial forces. The use of magnesium in material handling equipment includes application for dog power boards, grain sorters, and gravity conveyors. Next, 13.2 Corrosion resistant alloys. Non-ferrous metals and alloys are widely used in corrosive environments. At one end of the spectrum, they are used for water piping and food preparation. At the other end, they are vital to operation of many chemical plants dealing with aggressive acids and alkalis. Historically, titanium alloys have been used instead of iron or nickel alloys in aerospace applications because titanium saves weight in highly loaded components that operate at allow to moderately elevate temperature. That is figure 13.1. Next, cobalt or CO is used as an alloying element in alloys for various applications such as permanent and soft magnetic materials, superalloys for creep resistance and at high temperature, hard facing and wear resistance alloys, corrosion resistant alloys, high speed steels, tool steels and other steels, cobalt based tool materials, electrical resistance alloys, high temperature spring and bearing alloys, magnet storage stick alloys, special expansion and constant modulus alloys, biocompatible material for use as orthopedic implants or dental materials. Because the positive of titanium stems from the formation of a stable oxide film, an understanding of the corrosion behavior of titanium is obtained by recognizing the condition under which this oxide is thermodynamically stable. The Port-Baix or potential pH diagram for the titanium water system at 25 degrees Celsius or 77 degrees Fahrenheit is shown in figure 13.3, and the pitch the width regimen over which the passive TeO2 film is predicted to be stable based on thermodynamic or free energy considerations. Next, 13.3 Superalloys. Superalloys are a group of nickel-based, cobalt-based, and iron-nickel-based alloys that exhibit outstanding strength and surface stability at temperature up to 85% of their melting point or Tm, expressed in degrees Kelvin, 0.185 Tm Kelvin. The iron-nickel-based superalloys are an extension of stainless steel technology and generally are raw, whereas cobalt-based and nickel-based superalloys may be raw or cast. Depending on the application or composition involved, cast single crystal forms are often produced for aircraft applications. Superalloys are intended to prevent or minimize creep into formation at a high temperature. Figure 13.5. They all have a phase center cubic or VCC austenitic structure. Iron and cobalt both undergo allotropic transformations and become VCC, FCC at high temperature or with alloying. Nickel, on the other hand, is FCC at all temperatures. In superalloys based on iron and cobalt, the FCC forms of these elements generally are stabilized by alloying additions. Alloying elements include chromium, molybdenum, vanadium, cobalt, and tungsten. Next, nickel superalloys. Nickel-based superalloys currently constitute over 50% of the weight of the advanced aircraft engines. Turbine this component figure 13.6 are a major applications. Powder metallurgy processing of superalloys has proved to be very repeatable and a cost-effective method of production. Cobalt superalloys. Virtually all cobalt-based superalloys are alloyed with nickel in order to stabilize the FCC structure between room temperature and the solidus temperature of the alloy. Unlike other superalloys, our cobalt-based alloys are not strengthened by coherent ordered precipitates. Rather, they are characterized by a solid solution strengthened austenated or FCC metric, in which a small quantity of carbide is distributed. Cast cobalt alloys rely on carbide strengthening to a much greater extent. 13.4 Refractory metals. This family has 5 members, that is niobium, also referred to as a columbium, tantalum, molybdenum, tungsten, and rhenium. with the exception of two platinum group metals. Osmium and indium refractory metals have the highest melting temperature of all metals. Tungsten has the distinction of having the highest melting temperature of all elements, 3,410 degrees Celsius or 6,170 degrees Fahrenheit. Molybdenum or MuO has a relatively high melting temperature of 2610 degrees Celsius or 4730 degrees Fahrenheit, along with a high modulus, good grip strength, and the retention of mechanical properties at high temperatures. Molybdenum is primarily used as an alloying addition in iron, steel, superalloys, and corrosion-resistant alloys to improve hardenability, toughness, abrasion, resistance, strength, and resistance to creep at elevated temperatures. Niobium or Nb. In addition to its high melting point, niobium is used for its combination of relatively lightweight and retention of high strength at surface temperature ranging from 980 to 1205 degrees Celsius or 1800 to 2200 degrees Fahrenheit. Niobium alloys are also used to impede the passage of neutrons in nuclear applications. Rhenium. The properties of rhenium are generally similar to those of molybdenum and tungsten. Its melting temperature of 3180 degrees Celsius or 5756 degrees Fahrenheit is the second highest among the refractory metals. Pure rhenium combines superior low temperature ductility with good high temperature strength. It is used in combination with tungsten in the production of high temperature thermal couples. Next, 13.5 low melting point metals. Bismuth or Be is brittle, easy to cast, and not readily formed by standard working methods. It is melting point of 183 degrees Celsius or 360 degrees Fahrenheit is lower than that of thin lead solder. Bismuth is one of the few metals to increase in volume upon solidification. It is diamagnetic, slightly repelled by magnetic fields, and has allowed a capture cross-section of thermal neutrons. Indium is one of the softest metals easily extracted and highly plastic. It can be deformed in compression almost without limit. It melts at 156.2 degrees Celsius or 313.1 degrees Fahrenheit, has low tensile strength and hardness, and is stable in dry air at room temperature. It is neither a toxin nor a skin irritant. Lead. The properties of lead: high density, low melting point, corrosion resistance, malleability, unusual electrical properties, and the ability to form usable alloys and chemical compounds, combined with its readily available forms and relatively low cost, make it a unusual material for solving a variety of problems. Tin, one of the first metals known to humans, is non-toxic, soft and pliable, and suitable for cold rolling. Tin resists corrosion, making it an ideal casing for other metals. Tin has a low coefficient of friction, and the addition of alloying elements such as copper, antimony, bismuth, cadmium, and silver increase its hardness. Zinc has a relatively low melting point of 19 degrees Celsius or 787 degrees Fahrenheit. Resists corrosion, is ductile and malleable, and is highly soluble in copper. As a coating, zinc provides cross-corrosion protection for iron and steel. It is widely used in die casting parts for autos, household appliances, computer equipment, and builder hardware. Brass alloys are produced by mixing zinc up to 35% with copper. Next, 13.6 Reactive metals. Reactive metals readily combine with oxygen at elevated temperatures to form very stable oxides. Reactive metals are extremely noble because of their passive films. However, they may become embrittled by the inertial absorption of oxygen, hydrogen, and nitrogen. Hydrofluoric or HF acid rapidly attacks reactive metals such as niobium, tantalum, zirconium, and titanium, either as pure or alloyed metal. As low as 1 or 2% reactive metals in stainless or nickel alloys reduce their corrosion resistance to HF. Beryllium, titanium, liberum, tantalum, hafnium, and zirconium are considered reactive metals. Of their metals, beryllium and titanium are low-density metals and are often used for alloys in light structural application. As previously noted, niobium and tantalum have high melting point and are also classified as refractory metals. Hafnium and zirconium are similar in terms of chemical properties such as resistance to corrosion in nuclear environments and high strength. Nonetheless, there are two significant differences. Hafnium is not ductile as easily worked, while the ductility of zirconium is similar to stainless steel and alloys fabrication with common shop equipment. Next, 13.7 Precious metals. 8 metals are in the family. 2 of them, gold and silver, require little or no introduction. Not so well known as the 6 platinum group metals, which commonly occur together in nature: platinum, palladium, iridium, rhodium, ruthenium, and osmium. Gold is extremely soft, ductile, and easy to form. Chemical pure gold is 99.9% pure, and higher purity is commercially available. Resistant to oxidation is its outstanding property. It is colored yellow and maintained in air or when heated. Gold is usually allowed to increase its hardness because chemically pure gold is simply too soft for use in common applications such as jewelry. Silver. Among metals, pure silver has the highest thermal and electrical conductivity next to gold. It is the most ductile. Silver is also one of the most common corrosion-resistant metals. It can be worked, extruded, rolled, swagged, and drawn. Representative uses include electroplate, ware, sterling ware, jewelry and arts, photography, mirrors, and batteries, battery coins, and catalysts, which accelerate reaction in processing. Next, 13.8 Rare earth metals. Representative properties. Some rare earths can be fabricated cold, are poor conductors of electricity, and are paramagnetic, have little mutual magnetic attraction. Below room temperature, some are strongly ferromagnetic, have strong mutual magnetic attraction. Some form a thin oxide film under ordinary atmospheric conditions. As a family, the rare earths do not have properties that suggest usage as structural alloys. Scandium is similar to aluminum in density. While tritium has a density similar to that of titanium and melting point of 1522 degrees Celsius or 2772 degrees Fahrenheit, which allows a passage of neutrons and yttrium can be called organs. Samarium forms a protective oxide film in air at temperatures up to approximately 595 degrees Celsius or 1100 degrees Fahrenheit. Representative uses: rare earth metals are used in carbons for arc lighting. Mixed metal iron alloys serve as frames for lighters. Glass is polished with cerium oxide. Next, 13.9 Metalloids or semi-metals. Silicon used in industry can be classified into metallurgical and semiconductor grades. Metallurgical grade silicon is produced by the reduction of sand in an electric arc furnace. In content approximately 98% Sa. Metallurgical grade silicon is used primarily in the aluminum, steel, and silicon industries. Metallurgical grade silicon is also used for the production of colored stainless or fluorescent gallium or Ga. The chemical properties of gallium are between those of aluminum and indium, and like these elements, gallium is considered to any non-toxic substance. Its melting point is 29.78 degrees Celsius or 85.6 degrees Fahrenheit. Surface temperatures are increased by alloying, like aluminum. Gallium forms an oxide film on its surface when exposed to air, like water, bismuth, and germanium. It expands on freezing. Germanium is a hard metallic element with a lower melting point, that is 937 plus minus 1 degree Celsius or 1718 plus minus plus or minus 2 degrees Fahrenheit than silicon, which results in better fabrication properties below 600 degrees Celsius or 1110 degrees Fahrenheit. Germanium has a good resistance to oxidation. Above the temperature, oxidation proceeds rapidly. Next, 13.10 Special purpose metals and alloys. Uranium or U is a moderately strong and ductile metal that can be cast, formed, and welded by a variety of standard metals. It is used in non-nuclear applications largely because of its high density, 16% greater than that of lead. Uranium and its alloys generally are considered difficult to machine, requiring special tools and conditions. Next, vanadium. The melting point of vanadium is 1900 plus or minus 25 degrees Celsius. Chemically active and closely related to niobium, tantalum, titanium, and chromium. Vanadium is soft, ductile, and strong, and has good resistance to atmospheric corrosion and hydrochloric and sulfuric acid environments. Its cool working properties are excellent. In hot working, vanadium must be heated in an inner gas atmosphere. Magnetic alloys. Magnetic materials are broadly classified into two groups with either hard or soft magnetic characteristics. Soft magnetic material become magnetic by relatively low strength magnetic fields, and when the applied field is removed, they return to a state of relatively low residual magnetism. Next, essentially, a thermocouple thermometer is a system consisting of a temperature sensing element called a thermocouple which produces an electromotive force that varies with temperature. Although any combination of two dissimilar metals and or alloys will generate a thermal MEF, only standardized thermocouples are in common industrial use today. Table 13.3. These have been chosen on the basis of such factors as mechanical and chemical properties, stability of AMF, reproducibility, and cost. Okay, I think that's can I explain about chapter 13. If there are error in reading, please forgive me. And the last I want to say Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, salam nama budaya, and thank you.